So we introduced density operators or density matrices in order to describe situations where we don't have a definite quantum state, but a quantum state with some classical uncertainty. So in other words, we might have a probability Pj of having a state psi j. In that case, we construct this density operator, and from that density operator we can calculate anything we want to know, as typified by these expectation values, and we can also see how those density operators evolve in time. Now, one classic situation where we need density operators is after a measurement. Now, suppose I have a spin-half particle, and remember a spin-half particle just has two states, spin up and spin down. And suppose we start off in some superposition of spin up and spin down. Let's just make it an equal proportion of each. There we go, an equal proportion of spin up and spin down. However, we know that if we make a spin measurement, if we measure in this direction, this is say the up-down direction, then we're going to jump to either this state or that state. So what's the state after a measurement? Well, actually, we can't write it down using a state, because if we write up, we'll be missing out the idea that half the time it's in down. If we write this superposition here, we've got this plus I, and we know that if we then measure a particular state, like if we measure the spin in the y direction here, we'll get a definite answer. Whereas if we actually do a measurement in the z direction first, and we have up or down, then we'll get forwards or backwards in the y direction with equal probability. So what we really need to do is we need to write the state after the measurement as an equal probability mixture of being in spin up or spin down. And so the easiest way to describe the effect of a measurement is to use density matrices. But the main reason we use density matrices or density operators is when we're trying to describe a quantum system that's coupled to an environment in some way, but for whatever reason we don't want to be forced to describe the entire quantum state of the environment. We just want to focus on the state of the system, and so we want to ignore the state of the environment. Now, ignoring the degrees of freedom in a large reservoir environment means we've introduced the possibility of the system not being in a pure state. Instead, it might be in a classical mixture of states, and so we need to use the density matrix, just like we did for a measurement. Indeed, the Everett interpretation doesn't actually distinguish between those two situations in any way at all. Now, suppose our environment or reservoir is described by a Hilbert space, HR, and our system is described by a Hilbert space, HS. Then obviously the state of the whole system together is just the tensor product of the two Hilbert spaces. And any operator that acts on this combined system is a superposition of things that act on the system, tensor product with operators that act on the reservoir. But if we're only interested on the system, then we're only interested in calculating expectation values of system operators. Now, in fact, a system operator in this context is actually an operator on the bigger Hilbert space, but it's the trivial operator acting on the environment. So it's the system operator that we're interested in, tensor product with the identity acting on the environment. So how do we calculate these expectation values of system operators? Well, we know how to calculate the expectation value of any operator. We just take the trace of that operator acting on the density matrix and we're done. So we can do that in this case. Now, of course, our trace is over our combined Hilbert space, and so the basis states are every possible basis state for the system, tensor product with every possible basis state for the reservoir. This double sum represents our sum over all possible basis states for our combined system. So now we put in our operator. Now this operator here, the density matrix, is an operator on the combined Hilbert space, on the system and the reservoir together. Whereas these operators here only act on their individual Hilbert spaces. So we can pass these backwards, and this system operator will go straight through here and act on this part of the system, and this reservoir operator will act only on the reservoir things. And because the tensor product is completely linear, we can split up this double sum into two single sums. Now we've lost the tensor product symbol because this element here is in fact a system operator. The density matrix is a combined system reservoir operator, but when we take the inner product with all the reservoir states, all we've got left with is an operator on the system. And so we have the system operator we were trying to get the expectation value of in the first place, this A of S, multiplied by another system operator. Now we're going to give that system operator a name. So we're going to call that the reduced density matrix, or the reduced density operator. And as you can see, it is a system operator. We've noted that this sum over the complete set of basis states for the reservoir is just the trace. This is the trace over the reservoir. And when we take the trace of the reservoir of our density matrix, we get the reduced density matrix. And we can write the expectation value of our system operator AS very simply in terms of the reduced density matrix. So this trace over the system variables is exactly just this sum here. It looks just like the normal trace over the system variables. and we're acting on the system operator AS multiplied by this reduced density matrix. And you note that that looks exactly the same as the normal way you get the expectation value from a density matrix and an operator. So in fact, this reduced density matrix tells us everything we need to know about what we might get if we measure some system property. Now, of course, calculating the entire density matrix of the system and then tracing over the reservoir states is a cumbersome way of trying to produce the reduced density matrix. So if you're trying to only deal with a reduced density matrix, then you need to be able to find some situations where we can calculate the reduced density matrix without having to go through the process of calculating the entire state of the complete system, or we haven't really gained any advantage here. But it turns out there are situations where that can be done.